Okay, so yesterday we did our lab on velocity versus time graphs, which of course involved an accelerating object. Okay, the cart accelerates down the ramp because gravity is pulling it that way. Okay, so what we're going to look at today is what is acceleration and how do we use the formula for it. We've actually used it already in velocity versus time graphs, but only ever to calculate acceleration. We're going to look at how we use it algebraically to solve for the other three parts of the formula today, and then do some problem solving with it. All right, so first thing we need to understand is that for acceleration to occur, okay, for an object's velocity to change, there has to be something giving it a push or giving it a pull, okay, one or the other, right? There has to be a force acting. This has to do with Newton's first two laws, okay? Newton's first law says that an object at rest will remain at rest, and an object in motion will remain in motion at a constant velocity unless acted upon by an external unbalanced force. Okay? So in order for something to accelerate, according to Newton's first law, there has to be a force acting on it, a push or a pull that isn't balanced by anything else. Okay, otherwise, okay, nothing will happen, or nothing will change, I should say. Right, so for example, Newton's first law says that that cart will stay right there. Well, duh. Of course it's going to stay right there. There's nothing doing anything to it. Okay? Are there forces acting on it right now? There are. How many? Two. Right now there are two forces acting on this cart, but they're balanced. Okay, that word was in Newton's first law. Okay, it says that in the absence of an unbalanced force, it'll stay put or it'll continue to travel at a constant velocity. Right now, the force of gravity is pulling the cart towards the center of the earth. What's keeping it from going there? What's keeping this cart from falling? The ground, yeah. Okay. So gravity pulls the cart into the ground, and the ground pushes back up with an equal but opposite force. That's actually Newton's third law. You've probably heard this one before. Every action has an equal and opposite reaction. That's Newton's third law. Okay? It says that if gravity pulls the cart into the floor has to push back up with exactly the same amount of force. That way, they're balanced, and the cart doesn't move. Okay? If I give the cart a kick, it accelerates. Because that kick, that force, wasn't balanced by anything. There wasn't anything else acting to stop the cart from moving. Okay? If I put the cart against the board, and I push on it, now it doesn't go anywhere. Okay? Because gravity's pulling down, floor is pulling up, I'm pushing that way, board's pushing back, cart doesn't go anywhere. Okay? Now all the forces are balanced. Okay, everybody kind of follow on that? Okay, it's kind of obvious when the cart's not moving. The part of it that's weird is that an object will travel at a constant velocity forever, as long as there's no other forces. Do we ever see that happen? Like, if I get this cart moving, it did not appear to travel forever. What stopped it?
Friction.
Friction. Okay, there was two kinds of friction. There was the rolling friction of the wheels, and there was air resistance. It's not very aerodynamic. Okay, both of those forces were not balanced by anything, so they brought the cart to a stop. Did the cart's velocity change then? Then it accelerated. And it accelerated because there was a force, or forces, that weren't balanced that brought it to a stop, made it accelerate, made its velocity change. Okay, everybody all right with that idea? Okay, so acceleration, and this might help you with your hypothesis from yesterday, okay? Whenever the velocity of an object is changing, the object is accelerating. Okay, that is the definition of acceleration. Any change in velocity. in physics, we only use the term accelerate. Okay? In common language, accelerate means to go faster. Okay? In physics terms, accelerate means any change in velocity, speeding up or slowing down. Doesn't make any difference. Okay? Even, believe it or not, turning. Okay? Even if I go through a turn at 20 kilometers per hour, okay, I'm still accelerating. Why would that be? Think about this. Just out here where you take that corner that goes to the back parking lot, you ever see anybody landing the drink in there? Okay, go in the pond? Happens at least once a year. Somebody doesn't make that corner when it's slippery, okay, and they end up in the pond. The reason is you end up in the pond if you're A, going too fast, and B, there's not enough friction to accelerate you around the corner. Okay? It requires a force for you to turn because velocity is a vector quantity. It has direction. So even if all I do is change the direction of something, I don't make it go faster or slower, I'm still accelerating it. And that still requires me to push it or pull it. Okay, everybody follow? Okay, so any change in velocity is an acceleration. It doesn't even mean the object has to go faster or slower, it just means it has to turn. Okay, it could go faster, it could go slower, it could turn. All of those are examples of acceleration. Okay, now here's the good news for you. We don't deal with anything turning in Science 10, okay, because that brings trigonometry in. All right, we do that in Physics 20. Okay, but for this course, we'll simply worry about speeding up or slowing down. Okay, that'll be it. Okay, so the formula for acceleration goes along with its definition. Acceleration is the rate at which we change our velocity. Okay, that's why you see the change in velocity, Vf minus Vi, divided by time. Okay, acceleration is the rate at which we change our velocity. How many meters per second every second do we go faster or slower? Okay, just rip that thing open. And I'll only give you a little bit of a hard time about eating chips for breakfast. I would totally do that if I had a youthful metabolism. Okay, so everyone okay with the formula there? Okay, so all we do is take our final velocity, subtract our initial velocity, and then we divide that number by time. Okay? Everybody with me there? Now, here's where those units, those weird units that we've been talking about, the meters per second squared, here's where they come in. Okay? If on the top here, I'm going to have meters per second minus meters per second. So on the top, my units are going to be meters per second. And I'm going to divide that by seconds. Okay? Which again tells us acceleration is the rate at which we change our velocity. How many meters per second do you go faster or slower every second? Okay? That's why it's meters per second, or we sometimes write it like this. Okay? So if I take meters per second and I divide it by seconds, is that the same as seconds over 1? Is it okay to say that? Okay. If I want to divide fractions, what do I do to this one? Flip it. Right. I flip it and then I don't divide, but I multiply. All right, so what I end up with here is this. Okay, what's meters times 1? Meters. Okay, what's seconds times seconds? Seconds squared. Okay, you can write it either way. Okay, if you wrote an acceleration and you wrote meters per second, that's right. Okay, we usually write it meters per second squared, and we usually say it that way as well. Okay, everybody all right with that? So this formula here, okay, which we're going to use a lot today, actually calculates the average acceleration. Okay? It could be that the acceleration is actually different in a few places. This is going to calculate the average. All right, so let's look at a pretty simple example here. So let's say that we've got this plane right here, right? And it starts from rest. Okay, that word comes up all the time. Okay, if you start from rest, how fast were you going? 0. If you are at rest, you are not moving. Okay, so if you see the term or in a sentence of a problem, you say starts from rest, then your VI is 0. What if the object comes to rest? Then it stops. What's VF? 0. Okay, rest always means stopped. If you start from rest, then your initial velocity is 0. If you come to rest, then your final velocity is 0. Okay, it's just different ways of saying that. Okay, rather than the object stops. In physics, we use comes to rest. Okay, or if it starts, if it's standing still when it starts, we say starts from rest. It's just a physics way of saying that. Okay, makes us sound smarter, I guess, or something like that. Okay. All right, so in this situation here, the plane starts from rest. So its initial velocity is 0, okay, at time 0. The plane accelerates down the runway, and 29 seconds later, it reaches a velocity of positive 72 meters per second, where positive indicates to the right. Okay? Determine the average acceleration of the plane. All right, so if I'm doing that, here's what I know. VI is 0 meters per second. Time is 29 seconds. Okay? And I know that VF is 72 meters per second to the right. And I'm making right positive. Okay? So all I have to do then is plug into this formula, right? You've done stuff like this with the graphs. Okay, you found VF, you found VI, you divided by time, you found acceleration. Okay, so all we do is go A equals 72 minus 0 divided by 29 seconds. All right, that's going to give us meters per second divided by seconds, right? So we'll end up with 2.5 meters per second squared for the acceleration. Okay, so that means every second the plane will be going 2.5 meters per second faster than the second before. Okay, does that seem fast? It's about 1/4 of a G. Okay, right now, sitting in your chair, you feel 1 G worth of force. Okay, so you can feel the seat pushing on you as you sit on it with 1 G. So if you were in a plane that was accelerating at this rate, you would feel 1/4 of that force pushing on your back from the chair. Okay, pushing you forward. So it's really not that much force. Okay? And it's actually really not that super fast. Okay, everybody all right with how that works? Okay, so really what we need to get out of this first little bit here is to accelerate, a force has to be present. Acceleration is any change in velocity. And the formula is change in velocity divided by time. Okay, let's look at the algebra of using this formula. All right, obviously it's already set up to solve for A. So if we needed to solve for A, we don't have to do anything to it. Right? What if I wanted to solve for T? What should I move if I want to solve for T?
Do you have to connect it with the A, like switch the A and the T or no?
Yeah, I would absolutely switch the A and the T. Okay? I can't solve for T if I leave it on the right-hand side because it's on the bottom. I'd be solving for 1 over T if I isolated it. Okay? You always want to have something on the top by itself if you're going to solve for it. Right? So what I would do, since I'm dividing by T, if I want to move T over here, what do I do? multiply both sides by t. Okay, so if I multiply, whoops, if I multiply both sides by t, okay, t will come over here. All right, now I have t times a equals the change in velocity. All right, so what do I want to do with a now? Divide it over to the other side. Okay, that's not a very hard manipulation, right? It's just like v equals d over t, isn't it? We did exactly the same thing. All right, here's where it gets a little hairier. I want to solve for vf. What should I move first?
VI?
Not quite yet. T. Remember, this is where that third rule of algebra comes in. Okay, we haven't used it yet. Okay, but the third rule of algebra says move what's not attached first. Okay, VI is attached to VF. T is not. Okay, so I can move T first. So I'm going to do the same thing I did the last time. I'm going to move T over here. Now how do I get VF by itself? Add VI. Okay, so I'm going to move VI over here. Okay. Now I got VI plus T times A. Okay, so here's why this, if you're looking at that and going, oh God, I hate math and I'm not good at algebra. Okay, think of it this way. Sometimes it helps to think of this in more of a logical way. If I have this manipulation, T times A equals the change in velocity. Okay, so this is the change in velocity, that's the change in velocity. If I move VI over here, what I'm saying is my initial velocity plus how much I change my velocity equals my final velocity. Okay? That should logically make sense in our heads, kind of like this. If I go to work in the morning with only $5 to my name, okay, and I work for 8 hours and I make 150 bucks, okay, at the end of the day, I have $155 to my name. Okay? My change in money during the day was $150. I add that to what I started the day with, I have my final bank account balance. Okay? That's what we're doing here. Whatever we start at, VI, plus however much we change it by, that gives us VA. Okay? All right. Now, probably what is the trickiest one? Now I want to solve for VI. Okay? I could do that, and it'll work, but I have to remember one thing. Okay? So Thomas said do exactly what you did before, but move VF instead. Okay? Yeah, I can do that. Okay? But now, how do I move this over to this side? I have to subtract it. Okay? Because VF is positive here. Right? So if I subtract VF over here, okay, what I'm going to have to do is move these over. Okay? Bring VF over here. Come on. What am I solving for? Negative VI, which, as long as you can keep track of it, is fine. But that means if I solve for VI and my calculator spits out positive, VI is actually negative. What if it spits out that VI is negative? Then it's actually positive. I never get that right when I do it that way. I always forget that I solve for negative VI instead of positive. Okay, if you can remember that, there's nothing wrong with this manipulation. Okay, but here's what I do instead. Whoa, I'll go together. Oh, no, you're kidding. Okay, so here's what I do instead. Okay, I move T over to this side, just like we did here. Okay, then, this is going to seem weird, I add VI over to this side. Okay, now at this point, you're probably going, yeah, but that solves for VF, Coder. You're trying to solve for VI. We know you're old and forgetful, but. Okay, now, here's what I'm going to do. If I was doing like order of operations, would I multiply T times A before I add it to VI? So it's really just one number, isn't it? Can I subtract it over here? I absolutely can. Now I'm solving for VI, and it's positive. Okay, now, if that got a little confusing, walk this through in your head again, similar to the money situation from before. Okay, if I want to figure out how much money I had at the start of the day, I would take the money I have at the end of the day and subtract how much I made during the day. Would you agree? So 155 minus 150 tells me I started the day with $5. Okay, so if you want to talk it through your head logically, okay, that's the way you can do it. T times A is the change in velocity. So whenever you're moving it around, it's essentially VF minus VI. Okay, so if you're looking to solve for VI, VF minus the change. If you're looking to solve for VF, it's VI plus the change. Okay, and then you'll always have it. Okay. All right. Copy this one down. Okay, inspired by your track meet yesterday. Okay, copy this one down and write down your givens, and then we'll walk through it together. Okay, so let's look at this one. So the sprinter starts from rest. What did they tell me? Right. What's zero? Initial velocity, right. Okay, so VI equals 0 meters per second. All right, and they reach a velocity of positive 16 meters per second. What'd they give me there? They gave me VF, final velocity. Okay, positive 16 meters per second, and then they tell me that takes 4.5 seconds, so they gave me the time. All right, so this is the easiest one of these. I'm looking for the acceleration. All right, so in this one, I don't have to manipulate the equation at all. I'm just solving for A by plugging in my numbers. Positive 16 minus 0 divided by 4.5. Okay, what does that come out to? It's going to take a couple minutes for my calculator to fire up.
16.
Is it? 3.6? Something about that. Okay, and should that have a vector on it? It should, okay? Acceleration is a vector quantity. Okay, if I have positive 16 minus 0, it's positive 16 on the top divided by 4.5. That stays as a positive number. All right, so acceleration is a vector quantity.
I actually have a question how
Okay.
you wrote the squared. Like, is
That was the unit thing we just talked about a minute ago.
Oh,
Okay, when I go meters per second divided by seconds,
okay.
right, then I'm flipping this and I'm saying meters per second times 1 over seconds. Meters times 1 is meters, seconds times seconds is seconds squared. It means meters per second per second. So this sprinter, every second will go 3.6 meters per second faster than the second before. So after 2 seconds, he'll be going 7.2 meters per second. Okay?
Yes.
All right. Actually,
Wait, so then how do I know when S cancels out each other and when S is squared?
okay, so in this situation here, I have meters over seconds divided by seconds. Okay, the seconds are on the same side; they're both on the bottom, so they don't cancel each other. Okay, does that make sense? Like that's why we did this here. Okay, if I divide these two, I have to flip that and multiply, right? So the seconds are on the bottom together. They don't divide; they multiply. Okay. In this case, it's okay to memorize that the units for acceleration are meters per second squared. That's okay. All right, copy this one down, write down your givens, okay? Give it a try. I'll give you a few minutes, then we'll walk through it together. Okay, so in this one they're asking how long it will take. What are they asking me to solve for? Time. Okay, so time is the question mark here. Okay, will it take a jet to accelerate from rest? VI is 0. Okay, to positive 85 meters per second. velocity final, right? At a rate of positive 22 meters per second squared. That's acceleration. And this is where, guys, units are really important, okay? It's easy for people to mistake the 22 for one of the speeds if they don't know the units well, okay? Now it does, because acceleration is like way up here, okay? And then they say rate of this down here. They're separated by quite a bit. It's easy for people to forget that this is a rate of acceleration and these are the velocities, okay? Look at those units so you know you're writing down things in the right place. All right, so in this one, we're being asked to solve for t. Okay, so A equals VF minus VI over t. If I want to solve for t, I have to get it off the bottom. So I have to multiply both sides by it. Okay, so I'll have t times A equals VF minus VI. What do I do with A? Divide it over to the other side. All right, now I can plug in my numbers. So that would be 85, positive 85, minus 0, divided by positive 22. All right, so 85 divided by 22. If I obviously had you know what, I'll just do it the right way. 80, so I'll put this in brackets on the top, 85 minus 0. If you had an actual VI, you would need to enclose the top in brackets or do it first. If you don't, okay, it will divide that number by what's on the bottom and then subtract that from 85. Is that the same thing? It's not. So you have to outsmart your calculator, okay, by doing this. Okay, so we get 3.9 meters, or sorry, 3.9 seconds, because we're solving for time. 3.9 seconds. Okay, so a question like that, guys, I would give you a mark for your givens.
How do you know when to round up to like 2 decimal places?
Sorry, I did a significant digits thing, which is something we do at the 20 level. All of these numbers had 2 significant digits, so I made my answer have 2. It's not a big deal. If you wrote 3.87, that's fine. Okay, so you would get a mark for this. You would get a mark for choosing the correct formula, because by the time you get to your unit exam, you're going to have like 20 formulas you're going to need to know. Okay, you would get a mark for your manipulation. Sometimes they also give a mark for the plugging in of the numbers, and then a mark for your answer. So it's going to be between 4 and 5 marks most of the time, okay, for a question like this. All right, so we're doing the same thing here that we did with the mole equation, right? If I give you a new formula, we go through one manipulation of, or every manipulation of the formula. All right, so write that one down, put your givens down, give it a try, and then we'll walk through it together. So in this one, it says, what will the final velocity be? So I'm looking obviously for VF. Okay, so the race car starts at positive 15 meters per second. What did they give me there? That's initial velocity, right? So now it's not 0. Okay, and accelerates at positive 7.2 meters per second squared. Acceleration. Okay, for 6.5 seconds. Time. Okay, so A equals VF minus VI over T. So I'm looking for VF. What do I move first? T. Okay, so I multiply both sides by T. All right, how do I get VF by itself? Add VI, right? If I want to move something, I got to do the opposite. I want VI over here, okay? So I would add VI to both sides. So what I start with plus how much I change it by should give me my final velocity. All right, so we're going to have our positive 15 plus 6.5 times positive 7.2. Now, you don't have to put in the positives when you're doing this, but definitely put in any negatives, because that would be important. Okay, so times 7.2. Okay, now this one you can put all in a line. Okay, so you could go 15 plus 6.5 times 7.2. Okay, because in this case, I do want that done first, and the calculator will do it that way. All right, so after 6.5 seconds of accelerating at 7.2 meters per second, okay, that object is going to be moving at 61, actually 60, we'll say 61.8, okay, but technically 62 meters per second. Now, I calculated final velocity, so what needs to go here? A positive, yeah, okay. That, if you didn't put a positive on that, it would be wrong. Velocity is a vector quantity. Okay, the question specifically stated these are positive values, so you need to put a positive in.
For any question to velocity, do you have to make it like a positive or a negative?
Yes.
Vector quantity?
Absolutely. Any vector quantity, including the acceleration, right? They could put positive beside that. Okay. Now you're solving for something else. Give this one a try. Okay, so how fast was a boat traveling initially? What am I looking for? VI, right. Okay, if it accelerated to positive 30 meters per second, final velocity, okay, at a rate of positive 2.6 meters per second squared, acceleration. Okay, for 8.9 seconds. All right, so that would be time. All right, so there's our givens. Okay, obviously it's an acceleration problem. Okay, and right now, obviously that is a pretty easy step, choosing that formula. But as I said before, by the time we get to the unit exam and you've used almost every formula on the back of your periodic table, getting the right formula is worth a mark. Okay, that's why we give you also a mark for writing down your givens. It helps you decide, well, I can't use that formula because I don't have mass, or I can't use that formula because I don't have D. Okay, it helps you to choose which formula is appropriate. Okay, so we're looking for VI. So first thing I want to do is move T over to the other side. So I'll have T times A equals VF minus VI. Okay, the way I do it, and you don't have to do it this way. If you want to solve for negative VI, that's fine. I just never do. Okay, I'm going to add VI over to this side. So I'll have VI plus T times A. And that'll get rid of VI. And then I'm going to subtract T times A over to here. So now I'm saying the final velocity minus the change in velocity gives me the initial velocity. All right, so plugging in my numbers here, that would be 30 meters per second minus 8.9 times 2.6. All right, so 30 minus 8.9 times 2.6. All right, so the initial velocity of that, was it a boat? Okay, is 6.9 or 6.86 meters per second. And what do I need to put on that? What needs to go right here? Positive, yeah. Okay. It didn't come out negative, so it must have been moving forwards initially. Okay, questions on that one? That's the trickiest manipulation of the formula, hands down. Okay. All right, now I've got another one here. This one does have a vector trick. Okay, so pay attention to direction on this one. All right, write it down, give it a try, because we've gone through all the manipulations now. Okay, so I want you guys to actually try this one. I'll give you a little bit longer to see if you can come up with the answer. All right, so in this one, they don't put the positives and negatives beside the numbers. This is a more typical type of question, okay, especially moving forwards into 20 level kind of things. Okay, they use the context of the question to make you assign the positives and negatives. All right, so what I do in a question like this is I can see that there are two different directions. It's telling me the ball was rolled up the hill, but it's accelerating down the hill, which is what happens when you roll something up a hill, right? It slows down. That's because its acceleration is actually down the hill.
So down with the 2.1 being negative.
Exactly. The 2.1 is negative. So here's what I do in a question like that. If I can see from the context of the question that there might be or is a change in direction, I draw the hill and I go negative positive. I assign it right away, I make it clear to myself, okay? So I know when I'm writing down my givens, rolled up a hill, okay, so VI is positive 4.5 meters per second, okay? Or I write, instead of the positive, I write uphill, because I have the positive here, it's up to you. And I have acceleration, I'm making that negative 2.1 meters per second squared, okay? And what's the velocity after 3.5 seconds? So I'm looking for VF, and I'm told T. Okay, now, here's another thing that can help you out with this. If you're reading it carefully, from the context of the question, the final velocity should be either smaller and positive, or bigger and negative, or still smaller and negative. It's going to be one or the other. It's not going to be bigger positive, is it? Okay, that's what can happen if you don't make the acceleration negative. You'll get that the ball went faster as it rolled up the hill. I have never seen that happen. Been on this earth a long time, okay? Nearly half a century. And I've never seen a ball accelerate up a hill without help, okay? So if I just roll the ball like this, it's not going faster, okay, on its way up the hill. It's going to slow down and probably stop and then turn around and roll back down toward me, okay? I have to know in my mind that that's what's going to happen, that I can use to check my answer with, okay? All right, so it's obviously an acceleration question, so we're using this formula. Okay, we want to solve for VF. So first thing I'm going to do is move T over to the other side. Then I'm going to add VI over to the other side. Now I'm solving for VS. All right, so I'm going to take my 4.5 and I'm going to add it to 3.5 seconds times negative 2.1 meters per second squared, because it is in the opposite direction. Okay, so 4.5 plus 3.5 times negative 2.1. All right, that answer makes sense to me. After 3.5 seconds, that object has probably stopped, turned around, and started rolling back down the hill. Okay, so in my answer though, and here's another thing that's important for this question, did the question give me positive and negative as a direction or a vector, or did it give me up the hill and down the hill as vectors? It gave me up the hill and down the hill. You write negative on your answer, it's wrong, because it doesn't match the vector you were given. Did you have to use positive and negative? Yes, and you always do. But if the question doesn't say positive and negative, you have to give the vector the question gives. Okay, so in the end, my final answer here, okay, is going to be 2.85 meters per second downhill. Okay, mathematically, did that come out negative? Yes, but I drew that thing earlier that said down the hill is negative. To remind me at the end of the question, I need to write uphill or downhill as a vector. What if you wrote negative uphill? Technically it's right, but it makes no sense to write it that way. Negative uphill is downhill. So if you wrote negative 2.85 meters per second uphill, like Yoda you talk. But that's okay. I mean, it's still technically right, but it's backwards. Okay? But still, I mean, yeah, negative uphill is downhill. Yeah. So technically it's right, but just negative wouldn't be. Everyone following the difference? I know it's picky. Physics is picky. That's the nature of physics. Okay. All right, I'm going to give you a little bit of a break here, and then we'll give you 4 minutes within the classroom, and then we're going to try some more. Okay, so obviously if you've been using triangles to do manipulations, that time has passed. Okay, there is no triangle that will work for this formula, or most of the ones coming up after it. Okay, so if you're still struggling with the algebra, the manipulation of the formulas, please come in and see me. We'll go over those rules of algebra. But guys, the triangle, I know some well-meaning teacher somewhere along the way showed it to you, but they kneecapped you in terms of your ability to do algebra by not teaching you how to do it in the first place. Okay, triangles are the bane of my existence as a science and physics teacher. Okay, so please, if you're having trouble with the algebra, you gotta come in and see me, because there's no triangle that you can draw that will manipulate this equation. It has a plus minus in it. Okay? Triangles only work if everything is being multiplied and divided and is set up in the right order. Right? And as we move along, okay, we've got other formulas we're going to be using, like this one. I don't know what you're going to use. Maybe a dodecahedron or something? I don't know. Like, you're cooked if you're using a triangle and trying to manipulate that puppy. Okay? There is just no way that that is going to work for you. Okay? It's just, I'm sorry, but, okay? It's just not. So triangles are out, guys. Like, you just cannot use them anymore. And I want to help you. I want to help you. If you're not comfortable with your algebra, please come in and get it worked out. Algebra is not that hard. Okay? You're looking at a guy in front of you who makes it look like he can do math, but I struggle with math a lot. Okay? I tried to help my son as he went through math 10, and I had to I'm just going to get you a tutor. Okay? Because I couldn't do it. All right? It's been, well, way too long since I did that, so I don't remember any of it. Okay, and I was never all that good at math. But I can do algebra because I only have to follow 3 rules. I'm a rule follower. I can do that. Okay, and that makes that part of it fairly straightforward. Right? It's just a matter of getting the hang of using those 3 rules. Guys, as a guy who is not good at math, I'm not going to brag here, but I'm going to tell you this. I got 100% in university physics using those 3 rules of algebra. All you have to be able to do is understand what's happening and manipulate equations. It doesn't involve you having to do anything like you're doing in Math 10C right now. Okay? The stuff you're doing in Math 10C is way harder than anything you would be required to do in linear physics. You get to calculus physics, that's something else entirely. Okay? But as long as it's linear, it's just manipulation. Okay? And you can do it, because I can, and I'm not good at math. Okay? Okay. Copy this one down, give it a try. I just want to go through a lot of examples here today so that we see how this formula works, and more importantly, we get the hang of reading a story, okay, a story-based question, and getting what we need from it. Okay? All right. So you have an object thrown up in the air at an unknown velocity. All right. So that would be the initial then that is unknown. All right. It is in the air for 6.5 seconds. What did they give me there? Time. Okay, its final velocity is 2.4 meters per second down. Okay, so I'm going to go up, positive, down, negative. All right, and I'm just going to write here that VF is negative 2.4 meters per second. All right, acceleration due to gravity, which is of course what's affecting it, is 9.81 meters per second squared. Which way does gravity pull? Down. Okay, so we got acceleration being negative 9.81 meters per second squared. So that is the Earth global average, the acceleration due to gravity. Okay, so on average everywhere on Earth the gravitational acceleration is 9.81. Okay, it isn't actually that number everywhere on Earth. Okay, if you're at the equator it's more like 9.78. Here it's more like 9.83. Okay, so it's an average everywhere. Okay. All right, so those are the numbers we have. We're looking for VI. So trickiest manipulation, and we probably have a change in direction because we're told down for our final and up for our initial. Okay, so I better get a positive number when I do all this or I've done something wrong. Okay, that's the kind of checks you can use in your head from the context of the question. All right, so A equals VF minus VI over T. I'm looking for VI, so I'll multiply both sides by T. Okay, for me, I'm going to add VI over to this side, and then I'm going to subtract T times A over. So VI will equal VF minus T times A. So when I plug in my numbers, okay, I'm going to have this. VI will equal negative 2.4 minus 6.5 times negative 9.81. Okay, so if I go minus and then I'm subtracting this and one of these is negative, am I going to be subtracting a negative? I am, because 6.5 times negative 9.81 is going to be a negative number. And then I'm subtracting that from 2.4. Am I going to get a fairly big positive number here? Good, that means that I'm doing this right, because it did say it was thrown up in the air. Okay, so negative 2.4 minus 6.5 times negative 9.81. Okay, I don't know who threw this, but they should be in the major leagues with an arm like that. Okay, because that's really, really fast. 61, okay, meters per second, okay, is super fast. All right, so we'll say 61.4 meters per second. Up, exactly. Got to have the vector on there. Okay, you'd be surprised how many people on a unit exam will do all of that perfectly right. That part won't surprise you. And then forget up and lose a mark. Okay, always remember vectors. Super important. Okay, just making some sense? All right, so you do have to read the questions carefully. And these are pretty simple stories. Okay, when you get to physics 20, the stories become more complex and less interesting. And then you get to physics 30 and they become even more complex and even less interesting. You have to just read and read and read, okay, and get all of this information out of a ton of reading to do one question, right? So we're kind of training you for that. All right, try this one. Okay, make sure you write down all these examples. Having examples to look back at when you're studying is super helpful. What's the trick on this one? If you slow down, your acceleration has to be negative. That's the trick here, okay? I'm just kind of showing you the terminology that's going to be used because not every question is going to lay out positive and negative for you. It's going to use contextual values like slow down, speed up, uphill, downhill, forward, backward, and you're going to have to assign those positive and negative values to it. So the trick on this one is that the acceleration is negative. That's how you slow down. You actually accelerate backwards by slowing down. Or you slow down by accelerating backwards. Other way, I talked like you over there for a second. Okay. All right. Tomorrow, guys, start a class, graphing quiz. Okay, so it's your redo. All right, so take advantage. And then obviously we'll work on acceleration for the rest of that. I did put up the 2 acceleration practice quizzes. You can have a look at those. Okay, we'll see how tomorrow goes. Okay, if tomorrow goes poorly and we're really struggling with the acceleration, which I don't foresee that being a problem, then I'll rethink the quiz Friday. But for right now, treat it like you do have one on Friday because I do think that's the way it's going to go. Okay? That also means don't pretend you're really suffering tomorrow because I'll know the difference.